Okay, probably one of the most important circuits that you're ever going to come across in electronics. It's so simple that you'll think, what on earth is this lecturer talking about? Why is that so important? It's just two resistors. Well, first and foremost, those resistors could be impedances. In other words, they could be Zs instead of Rs. So what is the difference between a resistor and an impedance, or resistance and impedance? Anyone know? Okay, well you've got your standard symbol, haven't you? So you can have that, or you can have the IEEE picture. I think it was on one of our notice boards over there. So you've got two symbols for a resistor. What happens with the resistor is an ideal resistor has a resistance of whatever it's set to, maybe 100 ohms, but it has 100 ohms at 0 hertz and it has 100 ohms at 1 gigahertz. It has the same resistance regardless of frequency. That's not true with a Z. So a Z is an impedance. Listen to the two words. Resistance doesn't change according to frequency. Impedance is frequency dependent. Okay? And as soon as something's frequency dependent, life gets really exciting. Okay? Because it means you can't trust anything anymore. Now you may have come across the equations XL equals 2 pi FL and XC equals 1 upon 2 pi FC. If you haven't, it doesn't matter. But what that's telling us is we've got a way of calculating, if we now say that that's not R, but it's Z, we've now got a way in which we can calculate the impedances. Now the impedance is frequency dependent. The impedance is complex, but the impedance is frequency dependent. So really, really exciting stuff there. Okay, I'll move those, I'll put them in a box. So if you didn't know that, you can copy that down. Now let's take the case where it's not an impedance, it's a resistance, okay? So it doesn't change over frequency. So it's R1 and it's R2. All I'm trying to do is explain to you why that circuit on the board is doing what it's doing. And this is the reasoning why. So what I want to know is what's V out. Okay, I know what V in is because I'm putting it in there. It's a sine wave, right? So I know what the input is. And let's say, for the sake of argument, that's 10 volts, peak to peak. You know what an AC waveform looks like? It's just like that, depends whether it's sine or cosine. And it can have an amplitude, and in this case we're saying it's 10 volts, sorry, peak to peak, okay? So that's great. Now let's imagine that we actually just put DC in here. So into here we're going to put 9 volts because we can get a 9 volt battery, right? So 9 volts DC. Okay, you can all picture what that is, one of those little square batteries like we've got on the end here. It's not a Pro Cell standard 9 volt battery, yeah? So if I put that in there, I still want to answer the question, well, what's V out? Well, there's a lovely equation that does it, and it's just this. V out equals V in R2 upon R1 plus R2. That's it. So if you tell me what those R values are, I can tell you what V out is, just by using that simple equation. And really it's just the ratio of the two resistors, right? R2 upon R1 plus R2. That's called, and this is the magic circuit, called a potential divider. Why is it called a potential divider? Because some of the current goes down here and some of the current comes out here, right? So I can split the potential. Drop some of the voltage across here, drop some of the voltage across here, not that I usually want to drop it across here. I can control what the output voltage is according to the ratio of the two resistors I've got, right? A potential divider. Very, very powerful tool.